infinity. We'll be telling us this time about Hochschild cohomology and deformations.
Let me introduce the following notation. This is just a piece of notation. I'm going to write A prime when I'm being given an A infinity structure. We say, given an A infinity structure A that belongs to U of A, and given some kind of a family G, which just means it's a family GD, right? Let's say that I'm being given two of these. I'm introducing the following notation. I am writing A prime to denote this, which is going to be defined as the unique A infinity structure obtained by solving the A infinity functor equations recursively. And let me explain what it means. Let me say what it means. Okay, this is a definition. This is a notation. That means if I'm being given, right, we had an infinity functor equation, we had two infinity structures, and we had some kind of specification. What does it mean for something to be an infinity functor, right? But we can also do it in the opposite way. We have a bunch of maps that look like they're infinity functors. We can just search for the unique infinity structure that would make this into a quasi-isomorphism. Just solve the equation order by order. And this is exactly what we do. This is this piece of notation. Just means you solve the equation recursively, and you get a quasi-isomorphism here. That's all. Okay?
But probably you also want to say that G of A is a group.
Yes, and G of A is a group
which acts
on U of A. Yeah. This is a group of like reparameterizations. Okay.
Complication in the group is just like composition in the usual way you do for isomorphisms.
You just
infinity.
Yeah, just stick things one into the other.
As you do it for the infinity isomorphisms.
Yeah, just stick one into the other. Like how would you? Okay. So yes.
So you solve the equation to make this a functor or to make this as a quasi-isomorphism?
I've solved this. This becomes like a quasi-isomorphism.
Okay. It's actually an isomorphism.
I mean,
On the bar complex, you actually get an isomorphism when you simply conjugate this structure.
Yeah.
yeah, okay.
It's isomorphism.
Okay.
Yeah, I mean, okay. It becomes you solve the infinity like functor equation. Like these structures are compatible and induces like an isomorphism. Yeah. Yeah, that's exactly what I'm saying. It is just a collection of maps such that G1 is the identity and they look like this. This is all.
Uniquely defined A prime is a G infinity. It's infinity algebra.
A prime is an infinity.
That uniquely determined.
Yeah, exactly. That's all. Okay, so now we have this space, the big space, right, of A infinity structure, and we have this GA and it acts on U of A. So obviously what we want to do is take we want to take the quotient and study it. What would it give us? Well, it would give us the moduli space of all infinity structures up to this reparameterization. And inside this space, there is a canonical base point. What's the canonical base point? Well, these are things that like are quasi-isomorphic to the structure of the cohomology algebra. So this is the structure, right? When we consider A, this is a graded algebra. This means it's a trivial A infinity algebra. So it's an infinity algebra with all the higher mu's equal to 0. Just look at all, so this is a base point here, the quotient, right? Just look at all the things that like are quasi-isomorphic to it. Does it make sense?
Which cohomology algebra do you construct?
Well, I mean, we have the space of A infinity structures A that are made by mu1 is 0 and mu2 is this multiplication. If we take the cohomology of any of these structures, it would equal this fixed A that we fixed here. Right? Yeah. So this is, okay.
So now you consider this cohomology, which is a graded algebra, you consider it as a trivial A infinity algebra. You
Yes.
put back into the space, and this is the...
Okay, so everything is good. let me say, and I said that we have a C action. And this is just obtained by, let's say that I'm taking an A infinity structure, right, mu D. I'm cooking up a new infinity structure whose D component would consist of just scaling this. Okay. So this can also be thought in the following way. This is in bijection to write two pairs B F from A to H of B, while you quotient out by infinity quasi iso F tilde such that H of F curly equals F. This is by homological perturbation lemma that we've seen. Okay.
So the homology of A is equal to H.
Hmm?
Homology.
Yeah, this F from A to HB, this is a normal, like, where is the hat? Yes.
Okay.
Yeah. Okay. So far this is good. Yes. What are you asking?
What is this?
This is just a complex number. And what I'm doing is I'm taking one of these family of maps and I'm just scaling all of them, where the def component, the def map, gets scaled by epsilon d minus 2. Yeah, just multiply each of them by a number. That's all.
What is the goal? Why are we doing it?
Why are we doing this? Okay.
No, because if you put epsilon equals 0, you get exactly infinity algebra corresponding cohomology, because all higher mu will be 0. Epsilon 1 is not changed because 0 is 0. Mu 2 does not change because 2 minus 2 is 0.
Yes.
The rest will die.
And another, yes.
So I have a question about UA.
Yes.
What you wrote that mu minus 0 and mu2 is equal to m. So
Yes.
do you assume that mu3 and mu4 and all the others vanish or no?
No, this is exactly the point. They
Okay,
don't
so-
vanish.
So why do you, so now when you write here the quotient,
Yes.
you write FA maps to HB, but you wrote a little isomorphism sign over it?
Yeah, I'm saying all pairs, this is an A infinity algebra such that we end a fixed identification between its cohomology and A.
Right, but when you say the cohomology, just to make sure, when you say the cohomology, you don't mean with all the higher operations, you mean just with mu1 and mu2, or like just with
I mean, when we go to the cohomology algebra, we kill off like all this other higher stuff, right? We know how to pass the cohomology category from an A infinity category. And if you recall what
We
happened,
keep only
mu2. Yeah.
mu2.
But F is an A infinity function.
No. This F is curly, and therefore this is an infinity. This F is bald-faced. This is from A bald-faced to HB bald-faced, and this is just a normal functor of like, yeah. Okay.
Once again, is this a claim that you're going to prove now?
No, I'm breezing through.
It follows from what you said.
I mean, it follows from homological perturbation that was proved by, like, in the second lecture, right? This is
homological perturbation theory.
yes, this is a direct application of homological perturbation theory. So let me just say, okay, just two things that I want to say, which is, okay. I'll be very, very quick about it. Okay. An observation is that the Hochschild cohomology of an algebra, if you have a graded algebra, that's actually bigraded. and we introduce the following notation. These are just multilinear maps tau from A tensor S to A of degree equals T. Maybe I should, in sake of, these are, right, would it be more convenient maybe if I write them down like this? Yeah. You understand what I'm saying, right? This is clear to everybody? Just the grading, right? The grading is clear. This is degree T, and this controls the number of elements here, S. Okay. So the point is the differential, the Hochschild differential of an algebra, which is defined by bracketing with just M instead of a whole A infinity structure, actually preserves by grading, and we can write HHS plus T AA T. Okay. So now I want to define an obstruction class. HF is F, the fixed identification between the cohomology algebra and B.
Yeah.
Yeah.
I mean, how does that act on that? I think that advertised.
Hmm?
It's the same.
Quotients doesn't make sense, right?
F is it from B to B prime, like from curly B to curly B prime?
F is from A to the cohomology, and I'm looking at quasi-isomorphisms that lift this cohomology functor.
It's not a group.
Let's see if I'm doing something again that's
I think you want curly to go from B curly to B prime curly and to be the identity of the cohomology.
from B curly to B prime curly.
No, we play.
Yes, sorry. Yes, thank you. Yes, and it is compatible with the cohomology level. Right? Point is we have this identifications. Yes. So, and I want to have a quasi-isomorphism, yes, such that H of B prime, each of them, let's say it has an F, it has an F prime, this goes to A, this goes to A, this is the identity, this lifts. Yeah. Yes. Sorry. Okay.
That's H of F curly.
Yes, H of F. Thank you. Thank you. Okay. All right. So we have this. Okay. So let me introduce the following definition, which is I let U of A, if I have some A infinity structure, right, denoted U of SA, such that mu of S vanishes for all S's between T2 and some order D, then UD of A is a cocycle for the Hochschild differential of the algebra, which is obtained by M. Call its class OD of A, which is UD of A, sits inside. Sorry. This is A, the algebra. This is bald-faced. 2 minus D. This is the abstraction class of order D. So, two theorems that we need. So, we know that if HH2 A 2 minus D is 0 for all S, then U of A mod G of A equals the base point, which in more prosaic terms means that A is what's called intrinsically formal, which is here, and here is a definition. It means that any A infinity algebra curly B with an identification from HB to A as graded algebras is actually quasi-isomorphic to A, with its trivial, of course, A's with its trivial A infinity structure. Is that statement clear? Yeah. Okay, and okay, so this is the case where information theory is real trivial. We need a slight generalizations of that, which is when we have one-dimensional. Then we have just one direction. And what we need is theorem. Suppose there exists some D bigger than 2 such that HH2 A 2 minus D.
And I think the hypothesis of the theorem is the second Hochschild cohomology. I mean HH2 2 minus S.
Yes.
You need to go for S up to
All.
D or something?
For all.
For all.
For all
Well,
S.
Yeah, this is there is nothing there. And here there is something, just one thing. And this is when this is 0, when S is bigger than 2 but not D. Okay? And we suppose that there exists some curly A inside U of A such that U S A is 0 for 2S D and O D A is non-zero. These are the hypotheses. Then any A prime inside U of A is equivalent to epsilon of A for some epsilon in C. In other words, the C orbit of this A is actually all the space. You just
This I don't believe. Because you don't put any condition on higher homology degree bigger than D. So I don't see why.
What do you mean? No, this is S bigger than 2, not bigger than D.
Ah, okay, then I agree.
Yeah.
That's right, yes.
Yeah, that would not be true.
No, then
Yes. Okay.
and of course you want to say that A, yeah. Okay, good.
Okay, good.
That's-
Okay. And let me just
Yeah.
say like briefly how you do it. The idea is you do an order by order induction. You start the induction by assuming that you have managed. Let's call it a sketch. How much time do I have?
Minus 10 minutes.
Okay, let's call it a sketch. Okay. You start by assuming that you have managed to build G1. I mean, you start with some kind of a formal diffeomorphism GD, and you start fixing it order by order. You assume that you have managed to correct all orders up to order r minus 1. Then you look at your equation. You look at the leading order term in the A infinity equation for A prime, which is just D star, right, of the A that you're trying to fix. You see that this is actually corresponds to being a Hochschild cocycle, but all abstractions are vanishing, and therefore it's a Hochschild coboundary. Then you look at the infinity functor equations, and you see actually what we're saying that what you need to do in order to kill this another like mu A to the order of D is exactly to correct by a Hochschild coboundary. Luckily, no abstraction group. So Hochschild cocycle give you a Hochschild coboundary, you just correct it. And then now you have managed to fix up to R orders. You go again, and again, and again, and again, and again, and again. And the point is like this process stabilizes because at every point you just change something at order R minus 1. You just go over this diffeomorphism and you correct it order by order. And okay, let me just say quickly HKR and conclude because the last thing that I'm going to say is the HKR ISO. Well, you more know the original form 1962 says that if you have a commutative K algebra and you write X to be the spec of A and you assume that this is an affine smooth algebraic variety of finite type, then there exists some kind of an isomorphism, and this isomorphism goes from the Hochschild cohomology of A into the space of polyvector fields, where this just means the exterior powers of a tangent sheaf. So this kind of makes sense because now that we know that Hochschild cohomology actually tells us about deformations, this gives you a more geometric way of thinking about it. I mean, it really is vector fields. And we will need just a graded version of this, and a simple one, and I'm just going to write it down here. What we need is the following theorem. Well, let V be a fixed vector space, and we take A to be the exterior power of V, and let's pick some kind of a basis, which will be now theta 1 to theta n, and everything our field here is going to be assumed C. And let's consider the symmetric power of the dual, which is just this, where this is the dual basis of this, okay?
Are you considering formal power series or polynomials?
Formal power series. Then we have HKR map. It just goes from C star A to K Z1 to Zn theta 1 theta n, which can also be written as sim S V hat tensor S plus TV, and this map induces.
K is C.
Hmm?
K.
K is the the vector field. Yeah, the vector field is C, and this induces an isomorphism. Sorry, from Hochschild homology into this. And I'm just going to say what this isomorphism does, let's say, on a generator. If you have Z1, A1, Zn, An, and then you have theta 1 to the B1, theta n to the Bn, well, this is the same as the Hochschild map from A tensor S to A. Let me write down here a formula for the grading. This is just S is the sum of the AI, T is the sum of the BI minus the sum of the AI, and here this takes theta 1, A1 times, theta 2, A2 times, etc. This sends it to theta 1 to the B1, theta n to the Bn. So what you think is basically these are like, they're placeholders, but remember how many were there here. And the reason this works is because we use the bar resolution, right? We had some kind of an abstract definition, but we always use the resolution because it was so much nicer. But the point is, like, when you work with an algebra, you have another resolution, which is really nice, which is a Koszul resolution. And this Koszul resolution gives you just this. And this is how it all works. Any questions? Comments? If not, I'll apologize like profusely to Nick for stealing it.
Do you really need the forward power series, and is it 1 with n, or is it just polynomial function? Because I mean, it's kind of strange because they say that the Hochschild complex is the one you brought on the right-hand side.
Let me think for a second.
So it seems like strange, but it's just everything is fine today.
Do I need
If
for?
it's really sim, then I guess they're just going to polynomials.
Yeah, I think you're right. I don't. Yeah, I guess you're right. Okay.
You're trying to write here what this map is?
What this map does for a generator. It takes A1 of these and it turns them to B1 of these. Hmm?
Can you explain what this notation? I can't really read what you're.
Well, it tells you what this chain does on, like, this chain acts on A tensor S, right? And this has some kind of a basis. And it tells you what it eats and what it spits out.
But, I mean, this is the inverse of the HKR match?
You mean, yeah, okay. This is,
Is that what you wrote closed?
what do you mean? Let's see.
You apply the Hochschild differential to it, and then you get 0.
You apply the Hochschild differential to this, you get 0. Yeah. I think it is closed. It's just the inverse of, like, taking tau to, like, summing over tau s this formal z's when z is the sum of z1, right? zi theta I, and just expand it.
That one's the chain.
Yeah. I think. But let me just write down the formula in this direction. It's better. Okay.
We should have a coffee break.
Yeah.
If whoever wants to continue discussing this will
Yeah.
continue listening.
Yeah.
So coffee break until 12 o'clock.
Let's
So thank Natalie.